focused on analyzing and predicting bus breakdowns and delays using real-world operational data from New York City Department of Education's bus breakdown and delays dataset. The dataset contains detailed records of bus incidents, including timestamps, locations, route informations, reasons of delays, and the number of students affected. Our main objective was twofold. First, to understand the key patterns and factors contributing to bus breakdown, and second is to develop a predictive and model capable of identifying high-risk conditions that leads to such events. From a technical standpoint, we began with extensive data pre-processing. The raw dataset contained missing values, inconsistent text formatting, and non-standardized date and time fields. Using Python, Pandas, and NumPy, we standardized the dataset by converting timestamps into proper date-time format and numeric values. A delay duration. Text columns such as reason were normalized using regular expressions and categorical encoding to ensure model readiness. Next, we engineer new temporal and operational features such as hour of the day of the week, month, year, and weekend indicator. To uncover time-based trends, for instance, we analyzed how incident frequency varies across weekdays versus weekends, or how specific hours experience higher delays. Using Matplotlib, we visualized these relationships through bar plots, heat maps, and trend charts, allowing us to identify peak breakdown periods and major contributing causes, such as mechanical failures or traffic-related delays. For the predictive component, we formulated the problem as a binary classification task, predicting whether an incident would result in a breakdown or simply a delay. We utilized scikit-learn's machine learning pipeline for pre-processing, imputation, and model training, ensuring reproducibility and modularity. Among various algorithms we selected, XGBoost due to its superior performance on tabular data, handling of missing values, and ability to capture complex nonlinear relationships. We validated the model using stratified k-fold cross-validation to ensure generalization and evaluated performance using metrics such as ROC, AUC, precision, recall, and F1 score. To interpret the model's decision, we applied SHAP, Shapely Additive Explantations, which allowed us to identify the most influential features, such as time of day, route number, and specific delay reasons. Our analytical approach and model selection were driven by both accuracy and explainability. While algorithms like deep neural networks could have been employed, we opted for XGBoost and Shape because they balance predictive strength with interpretability, a crucial requirement in operational and policy decision-making contexts. In conclusion, our project not only demonstrates a robust analytical workflow, but also provides actionable insights for transportation authorities, helping them predict, understand, and ultimately reduce bus breakdowns incidents through data-driven strategies. Now, the rest of my teammates will explain how the model works from the code. Thank you.
Um, uh, Now I walk you through the data analysis I did. So first we prepared data for analysis. This involved loading the dataset, converting text-based dates into usable format, and most importantly, standardizing the delay times. We converted descriptions like 1 hour into a consistent numerical format like 60 minutes. Then we engineered two key features called delays VRT and estimation cost. We categorized each delay as minor, moderate, and severe. This will be our target for a classification model. Then estimated cost. We created a metric to translate delay minutes into a financial cost, helping quantify the impact of this instance. Then with our data prepared, we began our exploratory data analysis. First, our key insight is financial impact by operator. This chart shows that a few bus companies are responsible for a disproportionately high share of the total delay costs. This immediately tells us where to focus our attention for the biggest impact. Next, we look at the root causes. High traffic is the most common reason for delays. However, internal issues like mechanical problem are a close second, which points to opportunities for improvement in fleet maintenance. Then the third insight is this pie chart. Uh, this pie chart is particularly revealing. It shows that the vast majority of delays, nearly 85%, are severe, meaning they last longer than an hour. When delays happen, they tend to be significant. Then we dig deeper into the data, and we look for patterns over time and by location. These charts show clear seasonal and weekly trends. Delays are peak during the school years and most common during the weekends. And the next chart, uh, it importantly identifies the top 10 routes. The next chart. The top 10 routes with most frequent delays. These are the specific areas where operational improvements could be most effective. Uh, then we move to our predictive models. Our first model is a random forest classifier designed to predict the severity of a delay. After training on features like the company, reason, and location, our model achieved an accuracy of about 85%. This classifier report shows it's especially good at identifying severe delays. Then, to understand how the model makes its predictions, we look at future importance. It's very clear that the reason for the delay is the most critical factor in determining its severity, followed by the specific bus company. Then, our second model is a random forest regressor that predicts the actual duration of the delay in minutes. This model achieved an R squared value of 0.72, meaning it explains about 72% of the variance in delay times, which is a strong result. And just like our first model, the future importance plot confirms that the reason for the delay is most influential predictor of how long it will last. This is consistent and powerful insight for our modeling. In summary, this analysis has covered key areas for improvement, like from specific bus companies and routes to the most common causes of delays. The predictive models we built demonstrate a strong ability to forecast both the severity and duration of incidents based on initial information. These tools and insights can directly support more proactive and cost-effective operational management.
The main goal of our work was to understand why and when bus breakdowns happen and to find patterns that can help in predicting and reducing the breakdowns. We started with data processing, as the raw data has many missing values and inconsistent formats. Some columns like borrow and reason had blanks, so we fill columns with strings as unknown, and for numerical columns we have filled the empty values using the median. We also cleaned column names by converting all of them into lower cases, and also removed extra spaces, converted the date column into proper date time format, like year, month, date, and then the time of the day in 20 hours, 24 hours format. This allowed us to extract the month, weekday, hour of each breakdown, which in turn helped us to analyze time trends better. We also removed duplicates and extreme outliers, uh, with which the model can be affected in the negative way. And then we moved to feature engineering, by which we added extra columns which can be held for training our model. For example, from the date we created, month and weekday features. We also made a column called target breakdown to indicate if a breakdown happens or not. This was used later for machine learning. Another feature we created was PCT breakdown, which basically is the percentages of breakdown in each borough. Each borough refers to divisions in like different divisions in New York City. We also converted the text columns like borough and reason into numeric format so the model could understand them. After preparing the data, we did exploratory analysis to find patterns and insights. We noticed that breakdowns mostly happen in uh, boroughs like Brooklyn's and Queens. They were the most frequent on weekdays compared to weekends, which makes sense because there's more bus traffic on working days due to the school hours. The most common reasons for breakdown were mechanical problems and traffic delays. We also saw that in winter months, they had slightly more breakdowns, probably due to weather conditions, which affects the bus. Finally, we built a machine learning model using XGBoost classifier and regressors to predict the chances of a breakdown based on factors like borrow, month, and reason and delay duration. The model gave decent accuracy and helped us to identify which features were more important. We found out that reason for delay, borrow, and month are the main columns that had biggest influence on predicting breakdowns. And with our analysis, we showed that breakdowns are not random. They follow certain patterns across time and location. By cleaning and transforming the data properly, we could visualize these patterns and build a model that helps us in early prediction. With these insights, it helps a city transport department to take preventive steps, schedule maintenance better, and improve the reliability of bus services. And my friend Niranjan will take over for walking you through the dashboard.
Hello everyone. Today I'll be walking through our website, which has different labels shown, like the home page, overview section, dataset. The home page gives us a full overview of the project. It describes what the project is about, our motivation behind it, the dataset used, analysis and insights we derived, and the machine learning models we implemented. It also includes links to our GitHub repositories, one for our project analysis and one for our website source code. Next, the overview section. The overview section explains our vision to use the data-driven insights to improve public transport reliability and our core objectives like predicting bus delays and breakdowns and service planning. The dataset page. The dataset page provides a clear description of the dataset and its source and a download option for the CSV file. The data is redirected to the official New York Open Data portal data.city.newyork.us, ensuring transparency and authenticity. Moving on to the analysis section, we've included two interactive visualizations. First one, a line chart showing incidents per year, which highlights the trend of recorded incidents over time. And the second is a bar chart showing top boroughs, which identifies areas like Brooklyn and Bronx as having highest number of incidents. Next comes the ML models. The ML models showcase four major models we built. Delay prediction model using XGBoost with around 78% accuracy, breakdown prediction model, which anticipates bus breakdowns with around 72% precision, feature importance and pattern analysis, identifying key delays and breakdown factors, visualization and reporting, which turns model results easy to understand dashboards. Finally, Meet Our Team section acknowledges all the members who contributed to this project. Overall, our website brings together data analysis, visualization, and predictive modeling in one place, making complex information simple, visual, and actionable. Thank you.
Yeah, here we are seeing our dashboard, which contains two pages, where it is very user friendly for both users and as well as government companies, like government members, where they can get a ease of information, like in very easy manner. Like seeing here, we can see here KPI card. We used three KPI cards, where we can see like a total number of breakdowns that happened overall in the data set, and like here average delay, and here is total number of students that got affected from this bus delays. And here we have we kept two search bars, like one is for like they can search by using company name. If they choose the company that wanted, we can see that here this company have 10 breakdowns and average delay of 35, and total number of students got affected is 32. And this how with anyone can get the easy information. Like here we can see locations, like if we choose a New Jersey, in New Jersey we can see a total number of breakdowns happened and what was the average delay and what how many number of students got affected due to this breakdowns. And here we can see while we are changing this here the company name or a location, here we can see the changing of every chart will be get changed according to this search bars. Like here we can get the information like in which year how many breakdowns happen. Like here in 2010 in New Jersey we are seeing like 231 breakdowns happen. Likewise we can see information and we can get information. And when we come to this heat map, we can see the reasons behind these breakdowns. Like in New Jersey, we got 5,878 breakdowns. In that 878 breakdowns, most of the breakdown reasons was heavy traffic, and there are reasons like mechanical issues and a lot of issues like weather issues. We can sort it like what was the reason behind the breakdowns, and we can it will be very useful to get rectified those issues, and those reasons can be solved by using this information. And we kept a navigation bar, like detailed view of these things. Like the same thing here also works, like but here two extra informations that we will get, like like here we can see the pie chart which shows that number of breakdowns which related to the runtime. I mean in particular runtime how many breakdowns got happened. And if we see here, this is a matrix where we used for the root numbers, like in which particular root how many breakdowns happen. Like if we see here this 0008 something, this is the root number. There we see we have only one breakdown and it was the average of 23 minutes delay. Likewise here we can see 002, it is a root number and it is the number of breakdowns that happened in that particular route. And this is the average delay that is guarding at that route, that particular route. We can here also we can choose of like a location. If we choose like if we here I'm choosing like a New Jersey, we have if we these are the routes that which are related to New Jersey, and this is the information as we seen before 5878 breakdowns and 38.16 average days. The same information that we are seeing here, the same will be displayed here, but it will show related to the route numbers. This how we made our dashboard, which everyone can get ease of. I mean, very easily they can retrieve the information how the bus breakdowns are happening and how we have they have to go through across these problems, and it will be very useful to solve the issues that are happening in the bus journeys or bus related things which are having in the data set. This is how we build our dashboard. Thank you.